This is the first of two videos that present the solutions to the problems at the end of the flow unit. Written, complete, detailed solutions are already posted on Blackboard. So rather than writing complete solutions in this video, I'll explain the solutions and lay out the problems. Make sure that you take the time to think through these problems and write out the solutions for yourself. You'll learn the material much better that way, by thinking and writing it for yourself. So these are on page 130, and we'll start with problem number 1. It says water is flowing through a 6-inch ID pipe at a flow velocity of 20 feet per second. The pipe internal diameter reduces to 3 inches. What is the flow rate in the reduced section of pipe? So this is 6 inches internal diameter, and here it's reduced to 3 inches internal diameter. And we're told the velocity in the wide section of pipe, we'll call that V1, is 20 feet per second. And we're asked to calculate the flow rate. It's a bit of a distraction here. You'd think we wanted to calculate the velocity in the second section of pipe, but that's not what it's asking for. It's asking for flow rate. And recall that flow rate is constant. Right? Unless we have a drain or another input, flow rate is not going to change when velocity changes or diameter changes. And Q is simply A times V, area times velocity. So you can work with either section of pipe, and since we're given the internal diameter and the velocity for the first section, I'm going to say A1 V1, referring to the left-hand section here. So here's V1, it's given to us. And for area, we will want to calculate that. Area is pi d squared over 4. And we're given D1. So that's it. Just be careful to put your units in a consistent set of units. Looks like British units here. So the area would be square feet, and the velocity would be feet per second, and that would be cubic feet per second, which is volumetric flow rate in the British system. In problem number 2, we're told that oil flows through a 1-inch internal diameter pipe at a rate of 20 gallons per minute imperial, and a valve is placed in the pipe and has a passage of 0.75-inch internal diameter. What are the flow velocities in the pipe and through the valve? So I've labeled this up. Here's the internal diameter of the pipe and the internal diameter of the valve. We're asked to calculate velocities in both of these sections. Well, we know that flow rate is A times V, and we're asked to calculate velocity, so we're going to calculate V is Q over A. So whichever area you use, that would be the velocity you would use with it. We're given the flow rate, it's 20 imperial gallons per minute. And for the area, we'll use pi d squared over 4. Now, if you want area 1, we need diameter 1 to get velocity 1. So we're given D1 right here. Now, the only thing we have to be careful of here is to get a consistent set of units. So we need to convert this to cubic feet per second from imperial gallons per minute. And we'll have that divided by square feet, and that'll give us feet per second, and that'll be V1. To get V2, it'll be V1 times the ratio of diameters squared. And recall that the velocity would be greater in the small section of pipe, so V2 will be greater than V1, so make sure you put the larger diameter over the small diameter. And that'll be it for question 2. Question number 3, fluid is introduced into a pump through a 1.5-inch suction line and discharged through a 1-inch port. And the flow rate of the discharge is 40 imperial gallons per minute. What are the flow velocities in the inlet and outlet? This is just a lot like the last problem. What's V1? What's V2? Again, we're going to say that Q is equal to A times V. So just use a consistent set of areas and velocities. We can write that V1 equals Q over A1. And we're given the diameter, so we can write Q is over pi d1 squared over 4. And we're given d1 here is 1.5 inches. And we're given the flow rate here, Q, is 40 imperial gallons per minute. So this is simply a matter of using the correct set of units. You want flow in cubic feet per second, and you want the area in square feet, so that you'll get units of feet per second, and that would be equal to V1. So V2 will be equal to V1 times the ratio of diameters squared. And just keep in mind that diameter 2 is smaller than diameter 1, so the velocity will be greater in downstream of the pump. So V2 will be bigger than V1, and so put the larger diameter over the smaller diameter. Problem number 4 says if the discharge pressure of the pump in question 3 is 1500 psi, calculate the horsepower required to drive the pump and assume the inlet pressure to be 0, which simply means that the pump has to develop 1500 psi because it's starting from 0 and the discharge pressure is at 1500 psi. Right, so I've laid this out here. So for power, we use the formula P times Q, pressure times flow rate. And the pressure is given in this problem as 1500 psi. And in the last problem, problem 3, we're told the flow rate was 40 imperial gallons per minute. You'll need to convert these to a consistent set of units. So you'll want to convert 1500 psi to pounds per square feet. And in question number 3, you would have already calculated the flow rate in cubic feet per second, and that was found to be 0.1070 cubic feet per second from the last problem. And then pounds per square foot for pressure times cubic feet per second for volumetric flow rate will give you units of pounds feet per second, which is unit of power, and dividing by 550 pounds feet per second will convert it to horsepower. And that's it for question 4. Question number 5, we're told that a standpipe 50 feet high. A standpipe is simply a pipe that's standing upright. So here it is, 50 feet high, rests on top of a hill 135 feet above the level of a pumping station. So you can see this diagram is not to scale. And a pump sits in a pit 10 feet below the floor level. And the pump delivers 10,000 imperial gallons of water to the standpipe. So the pump has to lift the water 10 feet plus 135 plus 50 feet, or it has to lift 195 feet. What is the efficiency of the pump if it is driven by an electric motor of 600 horsepower? So first of all, what is efficiency? Well, the efficiency of a pump would be its power output divided by its power input or power consumption times 100%. No pump is 100% efficient. Anytime energy is converted from one form to another, there's some lost, typically due to friction. In the case of a pump, there may be slippage within the pump or, as I mentioned, friction. So the power input is the electrical demand of the pump, 600 horsepower. It's the rate at which electrical power is being consumed. The power output we're going to calculate using the formula power equals P times Q. We're given the flow rate is 10,000 imperial gallons per minute. You'll want to convert that to British units of cubic feet per second. And the pressure that the pump has to develop will be the pressure required to lift water 195 feet, and that's pressure. 195 feet of water is a certain pressure. You'll want to convert that to pounds per square feet. Recall that 1 atmosphere is 2,116 pounds per square feet, or 14.7 psi, and that's 33.9 feet of water. So you can use this term here as a conversion factor to convert 195 feet of water to pounds per square foot, multiply it by the volumetric flow rate in cubic feet per second. Units will be pressure, pounds per square foot, times flow rate, cubic feet per second, which gives you units of pounds feet per second, or foot-pounds per second, which is the unit of power. You want to convert that to horsepower. You divide by 550 foot-pounds per second. You'll get the answer in horsepower. Once you get your horsepower, that will be the output of the pump divided by 600 horsepower, which is the input, multiplied by 100, and you'll get a value, some percentage, that's less than 100%. Problem number 6. The ballast pumps in a submarine submerged at a depth of 100 meters discharge 20,000 liters per second of seawater. Neglecting losses, determine the horsepower required to drive the pump. Here's the submarine. It's 100 meters below the surface in seawater. So a ballast pump can pump water out of a lower compartment in a ship's hull. In the case of a submarine, presumably it pumps water in and air out when it wants to dive, and it pumps water out and air in when it wants to rise. So these ballast pumps have to overcome the pressure of 100 meters of seawater when they're pumping at that depth. And there's the flow rate. And the horsepower, we have to calculate the power of the pump. So you'd set it up like this. Looks like we're going to work in the SI system. So power is pressure times flow. We're given the flow is 20,000 liters per second. In the SI system, we want to convert that to cubic meters per second. And then the pressure that the pump has to develop is the 100 meters of seawater. Now it's a little greater than 100 meters of fresh water because the specific gravity of seawater is 1.027 times greater than that of fresh water. So 100 meters of seawater is equivalent to 102.7 meters of fresh water. Now in this equation we need to have units cancel. This will have to be units of newtons per square meter in the SI system. So we want to multiply by a conversion factor for atmospheric pressure that converts meters of fresh water to newtons per square meter, and that's the conversion. Atmospheric pressure is 10.33 meters of fresh water. You'll get a value in newtons per square meter, and that'll be the pressure. We then have the flow rate in cubic meters per second. Multiplying those units, you get Newton times meter per second. A Newton times a meter is a joule. A joule per second is a watt. We're asked to calculate that in horsepower, so you divide watts by 746 because there's 746 watts in a horsepower, and you get the answer in horsepower. Problem number 7. The fuel pumps in a ballistic missile deliver 1,500 kilograms per minute of liquid fuel, specific gravity is 1.47, to the rocket engine nozzles at a pressure of 2 megapascals. What horsepower must be delivered by the pumps? Well, horsepower will be power, which is pressure times volumetric flow rate. Now we're given here a mass flow rate. We'll have to convert to a volumetric flow rate of cubic meters per second, but we have the specific gravity, so we can do that. So I would solve it like this. Working in the SI system, power is pressure times flow rate. We're told the pressure is 2 megapascals. You convert that to pascals. Recall that pascals are newtons per square meter. Now the flow rate we need in cubic meters per second, we're given 1,500 kilograms per minute. You can convert that to per second. What about the kilograms to cubic meters, mass to volume? We're told the specific gravity of the fuel is 1.47. That means the density of the fuel is 1.47 times the density of fresh water. Well, the density of fresh water is 1 gram per milliliter, and that means the density of the fuel is 1.47 grams per milliliter. Or the density of the fresh water is 1 kilogram per liter, and therefore the density of the fuel is 1.47 kilograms per liter. Or you can say the density of fresh water is 1,000 kilograms per cubic meter, and therefore the density of the fuel is 1470 kilograms per cubic meter. So a couple ways you can convert this. You could simply say 1,500 kilograms per minute, and then convert kilograms to liters, because there's 1.47 kilograms per liter for this fuel, and then go from liters to cubic meters. Or you could go directly, say 1,500 kilograms per minute, and convert from kilograms to cubic meters, because there's 1,470 kilograms in a cubic meter. In either case, you'll wind up with a volumetric flow rate of cubic meters per second. So the pressure will be newtons per square meter. The flow rate is cubic meters per second. That'll give you newtons times meters per second, which, just like in the last problem, is watts. To convert that to horsepower, in the SI system, we divide by 746 because there are 746 watts in a horsepower, and there's your answer. Problem number 8 says seawater is being pumped up a vertical pipe at a rate of 150 imperial gallons per minute. Notice that the cross-sectional area of the pipe at the bottom is 10 square inches. Then the pipe narrows to a cross-section of 4 square inches at a point that is 330 feet higher. What is the pressure difference between these 2 points in atmospheres? This is an interesting problem. If we had a pipe, a vertical pipe, and the water was not moving, then the difference in pressure would simply be 330 feet of seawater. That's a pressure difference. Now, if the water is moving, and let's say the pipe is of constant cross-sectional area, it's not constricting, but if the water is moving up the pipe, then there would be an additional pressure loss due to friction. Now, we're not given a value in the problem that we could use, so we'd have to leave it out. But the fact that the cross-sectional area of the pipe is decreasing means that the velocity is increasing. And that's an increase in kinetic energy, and that's not for free. If the kinetic energy is increasing, that means some other form of energy is decreasing across this distance, and so that must be the pressure. The pressure must be dropping owing to the increase in velocity. And so that means we'll have to use the full form of Bernoulli's equation to solve this. So I've labeled this up: 10 square inches at point 1, 4 square inches at point 2. We're asked to calculate the difference in pressure between point 1 and point 2. We're given the flow rate is 150 imperial gallons per minute. So we'll need to use Bernoulli's equation, which I've written here: the pressure at point 1 plus elevation at point 1 plus the kinetic energy term, V1 squared over 2g at point 1, will be equal to the pressure at point 2 plus the elevation at point 2 plus velocity or kinetic energy term, V2 squared over 2g, and the head loss due to friction. Now, we're not given a pressure drop due to friction in this part of the question, so we'll leave that out. So the difference in pressure from point 1 to point 2 will be H1 minus H2. That's delta P. P1 will be greater than B2 because it's lower down. Can we get terms for this equation? Well, elevation 1, the lowest elevation, is always set to 0, and elevation 2, it will be 330 feet. We'll need velocity terms where we're given the flow rate and we have the area so we can calculate velocity. So velocity 1 will be Q over A1 and convert 150 imperial gallons per minute to cubic feet per second and convert the area from 10 square inches to square feet, and you'll have units of feet per second. Once you have V1, you can get V2 using the ratio of diameters. So V2 will be V1 times the ratio of diameters squared, keeping in mind that V2 will be larger than V1 because the area of the second part of pipe is smaller than that of the first. So you have your two velocity terms here, V1 squared over 2g, and here V2 squared over 2g. So that takes care of all your terms. Just rearrange H1 minus H2. So delta P is 333 feet of seawater. So we're asked to convert this to atmospheres of pressure. So we need to go to feet of fresh water. And bear in mind that seawater is denser than fresh water. So the height of fresh water that would exert the same pressure as 333 feet of seawater has to be a higher column, has to be larger because fresh water is not as dense. So multiply by the ratio of specific gravities to make this height get larger, and that's 342 feet of fresh water. Then you can convert from height of fresh water to atmospheres, and it's 10.1 atmospheres. Problem 9 says if there was a head loss due to friction of 3 feet between the 2 points in question 8, what would be the pressure difference? Remember I said they didn't give us a pressure drop due to friction? Well, now we have one for question 8. So we'll just add it in there. So now if the head loss due to friction was 3 feet, you recalculate and you'll find out that the difference in pressure is now 336 feet of seawater. Convert that to feet of fresh water and then to atmospheres, and now it's 10.2 atmospheres instead of 10.1. Question number 10. In the pump shown below, the flow at the outlet is 35 imperial gallons per minute. What is the flow at the inlet? What would that be? Kind of a trick question, right? Flow is constant. If the flow at the outlet is 35 gallons per minute, then the flow at the inlet is 35 imperial gallons per minute. Flow is not going to change unless we have a leak in the pipe or another input. It doesn't matter if the velocity changes, the flow is constant. If the fluid is water and the pump is 65% efficient and driven by a 5 horsepower motor, what is the pressure difference across the pump? Yikes. Okay, so this 5 horsepower motor is the rate at which the pump is consuming energy, but that's not its output. Pumps are not 100% efficient, so we're told it's 65% efficient. So to find out the rate at which power is being added to the system, you multiply 5 horsepower times 0.65. That's the effective horsepower produced in the system. But what's the pressure difference across the pump? Now, if the pipe diameter was unchanged, then we could calculate the pressure difference across the pump just from the information given here. We have the horsepower of the pump, we have the flow rate. Remember, power is P times Q, so using power and flow rate Q, we could calculate pressure, but we can't do just that because when the diameter changes, the velocity changes. That kinetic energy increase occurs at the expense of a pressure decrease. So to calculate this, we have to use Bernoulli's equation. Let's take a look at that. So here's Bernoulli's equation. We have the pressure provided by the pump, which we're kind of given. We'll figure that out. And then we have the pressure at point 1 plus elevation point 1 plus the kinetic energy at point 1, is equal to the pressure at point 2 plus elevation at point 2 plus kinetic energy at point 2, and then the head loss due to friction, which was not given in this problem. So we're actually asked to calculate the pressure difference across the pump. The pressure will be greater at point 2 than point 1. You want to calculate delta P as H2 minus H1. You can get it from this equation if we can get the other terms. So the elevation will be easy. There's no change in elevation across the pump, so those terms become 0. We'll need these velocity terms, which we should be able to get because we're given the flow rate and we have the diameters of the pipe sizes. We can get that. And we just need to calculate the pressure of the pump then and collect our terms. Let's start with the pressure of the pump. So recall that power is pressure times flow. We want pressure. So pressure is power over flow. Now we're told the power is 5 horsepower, but that's what it's consuming. Remember, it's only 65% efficient in what it produces. So multiply 5 horsepower times 0.65, and then convert that to units of foot-pounds per second. The flow rate is given as 35 imperial gallons per minute. Convert that to cubic feet per second. And when you do that, we'll get units of pounds per square feet. And the answer you see at this point is 19,100 pounds per square foot. But you can't put that unit into Bernoulli's equation. In this form of Bernoulli's equation, each term is in height of a fluid, the height of the fluid in the system. If you'd use the other form of Bernoulli's equation, in which all terms are units of pressure, you could put this value directly in, but not in this case. You'll have to convert it to height of fluid. So since it's water, use atmospheric pressure as a conversion factor. Recall that 33.9 feet of water is 1 atmosphere, and that's equivalent to 2,116 pounds per square feet. That'll convert 19,100 pounds per square foot to 306 feet of water, and that is the pressure that's developed by the pump. That'll be the term here, HP. Now the velocity terms, let's get those. Recall that Q is A times V, so V is Q over A. I'm using the values for position 1. I'll calculate velocity 1. Again, the flow rate is 35 imperial gallons per minute. You'll want to convert that to cubic feet per second. Now for the area, we're given the diameter, and that's pi d1 squared over 4. And remember to change diameter from inches to feet, and then you'll get square feet. Cubic feet per second over square feet. Velocity 1 will have units of feet per second. Then V2 will be V1 times the ratio of the diameter squared. So that'll give you the terms for V1 squared over 2G, V2 squared over 2G, and you should be able to then rearrange and solve for the pressure difference across the pump. It'll be feet of water. If it was then required to be in some other unit, you could convert it. Problem number 11. In the diagram below, water is being pumped up from a reservoir. A reservoir is a large pond or containment. The elevation at point 1 is 30 meters. At point 2 it's 33 meters. And then it's obviously the same at point 3, and it's 40 meters at point 4. We're given the velocity at point 3, which is 6 meters per second, and obviously it'll be the same at point 4 because it's the same diameter of pipe. An electric motor delivers 25 horsepower to the pump, but the pump is 75% efficient. So 25 horsepower is the amount of the rate at which electricity is being consumed. 75% of that is what will actually be converted to pressure in the system. If the head loss from 1 to 2 is 0.6 meters, and the head loss from 3 to 4 is 1.2 meters, now why don't they give us a head loss from 2 to 3? Well, you don't lose any pressure. You're actually gaining pressure in a pump, and that'll be included by that pump term. The question is, what is the pressure at 0.4 in meters of water? So we're going to digest this a little bit. So I've written some terms in here. Notice that the total head loss, described was 1.2 meters of water and then 0.6 for a total of 1.8 meters of water head loss, pressure drop. The diameter at 0.3 and 4 is the same as 1 inch. The velocity at 3 and 4 is the same as 6 meters per second. The diameter at 0.1 and 0.2 is the same as 3 inches, but look at this. V1 does not equal V2. I'm saying that V1 is equal to 0. Why is that? Well, think about this large pond. The velocity in the reservoir would be very, very minimal, nothing at all. So to solve this, we're looking for the pressure at 0.4. We'll have to use the full form of Bernoulli's equation because we have all these terms in there. We'll need the pressure provided by the pump, which we can calculate from 25 horsepower, 75%, and so on. We'll have the pressure at 0.1. Now the pressure at 0.1, I'm saying, is 0. What is the pressure at 0.1? Well, it's simply atmospheric pressure. We'll say, isn't that pressure? Shouldn't that be included? Well, no, because think about it. If we shut the pump off, how far would that lift the water up the system? It would only sit right here, right? It doesn't provide any lift to the water. So any lift to the water, any pressure that's provided by the pump is irrespective of atmospheric pressure. So no, don't include atmospheric pressure in this. We'll say the pressure at 0.1 in terms of the system is 0. The lowest point or lowest elevation is always set to 0. And we'll have a velocity term, but it's also 0 because the velocity is 0 at 0.1. That should be equal to the total mechanical energy at 0.4. We're trying to solve for the pressure at 0.4. The elevation at 0.4, we're given 40 meters at 0.4 and 30 meters at 0.1. The difference was 10 meters. The velocity at 0.4, it's the same as the velocity at 0.3, and that was given as 6 meters per second, so you can calculate this kinetic energy term. And then we have the head loss due to friction. We're given these two terms, which add to be 1.8 meters. So it doesn't look quite so bad when I put it this way, right? We have to calculate this pressure term provided by the pump. So we have the power of a pump is equal to pressure times flow. We want to solve for pressure. That would be power over flow. We're given the power is 25 horsepower, and that's the electric motor. That's the rate at which power is being drawn, but the amount or rate at which power is being delivered is only 75% of that, and you multiply that times 25 and you'll get horsepower. You want to convert that to watts because we're working in the SI system, and there's 746 watts per horsepower. You'll get units of Newton meters per second for the power delivered by the pump. We divide it by the flow rate, and that has to be then cubic meters per second. Flow is A times V. Since we have the velocity at 0.3, I'll use the area at 0.3. Now the area, we'll get it from pi d3 squared over 4. d3 is 1 inch diameter. But working in SI, so make sure you convert that 1 inch to meters before you square it and multiply by pi over 4. And you'll get an area in square meters. And you have the velocity is given in meters per second. It'll give you the volumetric flow rate in cubic meters per second. When you divide newtons times meters per second by cubic meters per second, you will get units of pressure, newtons per square meter. Now you can't put that term, that pressure term can't go in this form of Bernoulli's equation. In this form of Bernoulli's equation, every term is the height of the fluid in the system. And so you have to convert that to the height of the fluid. Now this fluid happens to be water, so that's easy. Use atmospheric pressure as a conversion factor. There's 10.33 meters or height of water that exerts atmospheric pressure, which is 1.013 times 10 to the 5 newtons per square meter. And that'll give you the height of water, which is this term here. Combine those all together, solve for H4, and you'll find that it's 454 meters of fresh water is the pressure at 0.4 in the system. And if you were asked to convert that to PSI or kilopascals or whatever unit or inches of mercury, you could do that from there. Problem number 12. A 45 centimeter ID pipeline carries oil with a mass density of 0.7 grams per mil at an average velocity of 3.60 meters per second. If the pipe narrows to 30 centimeters ID, what would be the velocity in the narrow portion? Well, I'm going to bet that it's greater than it was in the 45 centimeter pipe because it gets narrower. This problem really seems out of place. Probably should have been at the beginning, but let's solve it. So here I've drawn it up. We have a 45 centimeter ID pipe with a velocity of 3.6 meters per second for the oil, narrowing to 30 centimeters ID. Calculate the velocity. We know the velocity is going to be greater because pipe is narrower, so V2 will be V1 times the ratio of diameters squared, putting the larger diameter over the smaller diameter. And you want to convert those to meters and meters per second. And you say, what about the density? Why is that given? Well, really it's irrelevant. It's not going to affect the flow rate or the velocities, and maybe it's just there to make students think. All right, that's good enough for that one. Question number 13. A piping system is constructed of Schedule 40 steel pipe. We have a 3-inch pipe that carries water at a velocity of 50 feet per second, and a 2-inch pipe that carries water at a velocity of 25 feet per second. Both the 2-inch and the 3-inch pipes flow into a 6-inch pipe, Schedule 40. What is the velocity in the 6-inch pipe? You want to be careful here. This is tricksy. Can you just add up those two velocities and say the total velocity is 75 feet per second? Would it matter on the size of this pipe? What if it was a 20-inch pipe? Would the velocity be the same as a 6-inch pipe? Hopefully you see that's not true, is it? You can't just add the velocities. What is true though? You can add the flow rates. If you had, say, 2 liters a second coming from pipe 1 and 1 liter per second from pipe 2, then you could say that the total flow rate is 3 liters per second. Flow can be added, but not velocities. All right, let's try that. So I've drawn it up here. Notice that I said V1 plus V2 does not equal V3, but Q1 plus Q2 equals Q3. Now for the 6-inch pipe, the total flow will be the sum of that from the 3-inch and the 2-inch pipe. These flows will be area times velocity plus area times velocity. The velocities were given. They were 50 feet per second and 25 feet per second. But we need the areas. We're given diameters. Now, the diameters are not the actual diameters. It was said that it was a Schedule 40 steel pipe. And that means you have to get the actual internal diameters, and you have to use a pipe table to do that. Page 129 in your notes. So this is an example of a pipe table. The pipe described is Schedule 40. And Schedule 40 is a standard wall thickness. Schedule 80 is double wall thickness, and there are many other schedules as well, but we're going to deal with just with these two for now. Schedule 40 steel pipe. For a 3-inch pipe, that is the nominal size. That's what it's called or named as, but that's not the actual internal diameter. We have to calculate that. So from the table you can see that Schedule 40, the outside diameter is the same for both Schedule 40 and Schedule 80, it's 3.5 inches. Then we have the wall thickness. In the case of Schedule 40, it's 0.216. So we'll have to subtract 2 wall thicknesses from the outside diameter to get the inside diameter. So the ID is equal to the OD minus 2 wall thicknesses. I did the first one here for you. This was a 3-inch nominal size. The outside diameter is 3.5 inches minus 2 wall thickness is 3.068 inches. So you can see it's quite close to 3 inches, but it's not exact, and it would certainly be different for a Schedule 80 pipe, for example. You want to convert those diameters from inches to feet. Then when you get the area, pi d squared over 4, it'll become square feet, times the velocity in feet per second gives you the flow rate in cubic feet per second, and that'll be the sum of those two gives you the total flow in pipe number 3, and we're asked to solve for the velocity, which is Q over A. we just determine the flow rate total, and you'll want to calculate area 3 the same way we did for area 1 and area 2. Cubic feet per second divided by feet squared will give us velocity 3 in feet per second. So not difficult, but tricky if you're not thinking about the difference between velocity and flow rate. Problem number 14 says that crude oil with a specific gravity of 0.8 at a rate of 3,000 pounds per minute flows in a channel that is 3 feet wide and 18 inches deep. If the flow occupies exactly 1/2 of the depth of the channel, what is the velocity of the crude oil in feet per second? So this is the classic Q equals AV problem. We're asked to calculate velocity, that would be Q over A. We're given the flow rate, 3,000 pounds per minute, but that's a mass flow rate. We're given a density, so we should be able to convert that to volumetric flow rate. And then we're given some dimensions on this channel. It's not a circular pipe, but given the dimensions of 3 feet wide, 18 inches deep, and it's half full of oil, we should be able to calculate the cross-sectional area. Let's take a look at that. Here I've drawn it up. We're saying V is Q over A. Let's look at the area first. The area that the oil occupies, we're interested in its cross-sectional area. So that would be 3 feet across, and the channel or depth is 18 inches, but it's only half full. So that's 9 inches. So the area, cross-sectional area, is length times width. That would be 3 feet times this many feet. 9 inches divided by 12 inches per foot is 0.75 feet. That'll give us the area in square feet. We need to calculate the flow rate. It's given us 3,000 pounds per minute, but we need cubic feet per second. So how do we go from mass flow rate in pounds per minute to volumetric flow rate in cubic feet per minute? Well, the specific gravity of the oil is 0.8. It's typical, right? Oils float less than water. So if the density of water is 62.43 pounds per cubic foot in the British system, then the oil is only 0.8 of that. So 0.8 times 62.43 is 49.94 pounds per cubic foot. So this now is a conversion factor between mass and volume for that oil. So we can take our 3,000 pounds per minute, multiply it by 1 foot per 49.94 pounds, and we'll get then cubic feet per minute. Convert that to cubic feet per second. That's our flow rate divided by area in square feet will give us the velocity in feet per second. Problem number 15. The city water main supplying a large apartment building has a maximum pressure of 51.5 psi absolute. Here it is. That's the city water main that's coming into the building. The water taps on the top floor of the building are at 150 feet above the water mains. That's quite high. Calculate the maximum pressure available at these taps in psig. So the person on the top floor, they open their tap, they need water to come out, they need it for a shower, they need it for run their dishwasher. How much pressure will they have? One of the things you have to keep in mind is that when you open the tap, it's pushing against atmospheric pressure. You don't really have 51.5 psi to lift the water because you've got to push against atmospheric. What you want to know is how much gauge pressure do you have to lift the water so that when you open the tap, you get water out. So I've drawn it up here. So I want to know how much gauge pressure this is actually delivering. So gauge is absolute minus atmospheric. Absolute was 51.5. Subtract 14.7 psi. So they actually only have 36.8 psi gauge to lift water and push water out of a tap when you open it up. And there's 33.9 feet of water for every 14 psi. So they could actually, this system will actually only provide water 85 feet high. So if this is a 20-story building, maybe the people on the 15th floor are okay, but the people on the 20th are out of luck. So the penthouse suite should cost less, right? if you want to push water 150 feet high, you'll need equivalent amount of psi, which will be 14.7 over 33.9 times 150. You need 65 psi gauge. If we add atmospheric to that, the city water main would require 79.7 psi absolute. And that's probably not realistic. This is a real situation in many cases, and often apartment buildings do not get enough pressure to lift the water to the top of the floor. What do? Well, they have to have their own pumps to supplement city water pressure. And then they would have a reservoir on the top of their building. In the event that, say, power went out and the apartment building's pumps went out, the people can't be starved of water, so they pump it up to a reservoir on the surface of the tall building, which feeds to the floors below. And then when the electricity comes back on, the pumps can refill the reservoir on the top floor. So this will be a good place to stop for this first lecture on solving problems in flow. We have one more lecture involving problems 16 through 21.